and welcome everyone to today's Synergist webinar, PFAS, State of the Science and Regulation in Air and Industrial Hygiene. I'm Ed Rutkowski, editor of the Synergist, the magazine of AIHA. I'd like to thank all of you for joining us today, and especially SGS Carlson for sponsoring this webinar. Today's speaker is Bharat Chandramouli. He is Product Director for SGS North America and a senior scientist with 20 years experience in persistent organic pollutants and contaminants of emerging concern, or CECs. He is a published author on peer-reviewed articles and book chapters on atmospheric chemistry, PFAS analytical chemistry, CEC occurrence and fate, metabolomics, and more. Now I'll turn the presentation over to Bharat.
I'm going to share my screen now, and just so give me a second here. All right, hope you can all see the screen okay. So as Ed mentioned, I'm going to be talking about PFAS, focusing mainly on air and industrial hygiene, but there will be a few tidbits, especially on regulation policy from the other parts of the environment, because in many ways that's where policy is leading. So let's get started right away. A little bit about what the webinar is going to be. I will start off with a quick definition. At this point in time, most people know what PFAS are, so I'm not going to spend too much time on it, but as you will see, definitions will matter here. So we'll spend a little bit of time on who's defining PFAS as what and how that has implications, especially in the industrial hygiene area. We'll talk a little bit of, we'll spend a little bit of time on the overall regulatory picture, especially focusing on industrial hygiene, but also touching upon water, soils, what is happening. PFAS is a hot topic on regulatory front, so I'll provide a quick update, and hopefully it hasn't changed since I did my presentation last week because it's moving really fast. Spend quite a bit of time on measuring PFAS, especially in the emerging areas of air and occupational exposure. This is where there's a lot of research, a lot of standardization on methods going on as well. So I'll give you a brief overview of who's doing what and what the status of all these methods are. And then finish up with occupational exposure, who's exposed to how much PFAS, what the gaps are in understanding what to measure, how to measure it, and where we should be measuring. So that's going to be the general focus of the webinar, and hopefully some time for questions as well. So a little bit of background. I think everyone here hopefully knows what a PFAS is by now. It stands for per and polyfluoroalkyl substances. Essentially, things with fluorine in them, organic molecules with fluorine in them. The reason I put this kind of box chart here up front is that immediately you start seeing a dizzying array of different types of PFAS, because depending on structure, there's many different types of PFAS that are in use, or degradation products, or otherwise. Anything from a few thousand people have counted, depending on definition, to one preprint I saw a couple of months back, which listed it as greater than 1 million as the number of fluorine-containing substances in PCAM. So you'll see lots and lots of different structures. Also, in the last 5 years at least, the definition of PFAS is extended to include polymers. Typically, this always used to be only small molecules, but now fluoropolymers, side chain fluorinated polymers, all of these are considered PFAS as well. So, the definitions keeps expanding and the structure types keep expanding. So definitions, and typically when we talk chemistry, definitions are fairly straightforward. We all know what a PCB is, we all know what a pH is. PFAS definitely not as clear. Different jurisdictions have different definitions of PFAS, and this has pretty big implications when it comes to measuring and regulating PFAS. The EPA's definition is the most conservative, or the least conservative, depending on which direction you're looking at. It says at least 2 continuous carbons containing fluorine, where at least one carbon is fully fluorinated and the other one is only partially fluorinated. So what this means is that it needs to be a little longer chain, so at least 2 carbons containing fluorine to PFAS, which may leave out certain fluorine-containing substances like trifluoroacetic acid or a carbon tetrafluoride, for example. The OECD and Canada, which I forgot to include in the slide, I'm from Canada, mentions that the definition of PFAS includes only one fully fluorinated CF3 or CF2. So this is a more expansive definition that includes trifluoroacetic acid, as I mentioned before. Again, the number of PFAS or the number of fluorinated substances you consider PFAS really changes depending on whether it's one carbon, one fluorine, and how these definitions are are defined and how the regulation brings them into effect. The EPA has actually not finalized this definition yet. This came about a few years back. There's talk of a couple of different alternate definitions coming through the EPA as well to include more PFAS or in some cases define them as a case-by-case basis, depending on the type, the PFAS family, because as you see, the kind of the range of structures, just the breadth of this issue becomes very difficult to regulate. So the EPA is looking at multiple different versions of this definition of PFAS. So again, usually definitions are not this contentious, but in the case of PFAS, they definitely are. So yeah, as I mentioned, lack of global consensus on what's a PFAS. Exposure. So why are PFAS such a big issue? First off, they're used in multiple, many different types of products, as you know, consumer products, industry products, for example, aqueous film forming foam, for use for chrome plating foam for protection of mist suppressants in foam, for example, multiple different uses, industrial and consumer, waterproofing and more. So you see PFAS everywhere, and all of these PFAS are different in structure. What they all have in common is that because of the carbon fluorine chain, most PFAS are persistent in the environment. They may transform into other PFAS over time, depending on the structure, loss of oxygen or some breaking on a carbon hydrogen part of the molecule. But overall, that carbon fluorine chain largely remains intact, so just shortens over time. So that's one major issue with PFAS is their persistence. The other issue is causes toxicity, and we'll talk about that in a second. But people have been measuring exposure of PFAS for quite a few years now, and this paper by LC Sunderland et al. 2019 is a very good overview of the multiple different routes of PFAS exposure, of where you get exposed to PFAS from. And the table to the right of the screen here kind of breaks that down by specific PFAS. And you can see this is a fairly short list of PFAS. This is only the longer chain carboxylic and sulfonic perfluorinated acids. So these are the main, typically have been the main focus of research before PFAS, longer chain carboxylates and sulfonates. So you can see that depending on where you are and depending on who's done the study, depending on the population, the variation in the exposure patterns is quite stark. In most cases, diet happens to be the biggest source of exposure. So you can see multiple studies here where you go from 100% PFAS coming from the diet to 85%, 86%, 66%. But there are some studies which show that inhalation and dermal exposure are a fairly significant fraction as well. So 15% dermal, not as much, less than 1%, but inhalation in some of these studies can contribute up to 15%. And this is where industrial hygiene and built environment, this is where this becomes a major issue. But for most people, it is diet, it is tap water, and that water is a major source of regulation and regulatory focus in the US at the moment, and diet as well, especially through meat and fish. Diets heavy in fish will show high PFAS exposure for people. So again, lots and lots of different sources of exposure and many different exposure modes as well. The diet and tap water are the most studied. Dust and inhalation, not as well studied, though as you can see, dust has a fairly significant fraction as well. One more thing before I leave this slide is that it varies by the type of PFAS in the structure. PFBA, for example, you can see that's fifth from the bottom, is a shorter chain PFAS. It's a C4 PFAS, and you can see that most of that will be in the aqueous phase. So most of that is going to be in the tap water, whereas a longer chain PFAS, this C10 PFDA or the C12 PFDODA, most of that's going to be diet because it's long chain partitioning into the solid phase. So again, depending on the structure, depending on the population, exposure varies. Why are these a big health issue? There's multiple different health effects. We've been studying liver issues, we've been studying cancer issues. One of the major issues and one of the major targets here, and the reason why some of these limits are ridiculously small. So in this case, the EPA health advisory for PFOA is 0.004 parts per trillion in drinking water based on a lifetime exposure. And that, if you're a measurement scientist at all, is about 100 times lower than what we typically measure. And so the EPA's limit essentially is zero. These, uh, these really low numbers come from immune responses. For example, suppression of tetanus vaccine response, suppression of other vaccine responses as well. So that's why, I mean, and these are based on epidemiological studies. That's one of the reasons why these numbers are very, very low. And at these low levels, PFAS, especially these particular PFAS, PFOAs, are ubiquitous in the environment at backgrounds higher than these levels, and which is why they're persistent, widespread everywhere, major issue to remediate, measure, and deal with. Just because the epidemiology and the toxicology has led us to these extremely low numbers on these persistent chemicals. So essentially zero, just like lead for PFAS and PFOA. Again, these are interim advisories and still going through finalization, but we'll see where that takes us. When it comes to looking at PFAS, especially in the air, volatility and water solubility becomes very important, especially the Henry's law and vapor pressure. So depending on, and PFAS is a major issue with PFAS, of course, is that most of the PFAS of concern are anionic in the environment. So they're extremely water soluble. And so they tend to move to the aerosol phase or the solid phase quickly. But if you look at PFOA, for example, you would classify it as a semi-volatile depending on the model you use, depending on how you measure it. Again, it's complicated because of the ionic state, but they're not very volatile. They're fairly resistant to evaporation. For example, a fluorotelmer alcohol, which is a neutral PFAS, which is a bit more volatile, can be classified as closer to naphthalene, whereas PFOA in the acid phase, is closer to a TCE or a benzene. So again, depending on the structure, you see this wide range of volatility. And as I mentioned, a lot of this is complicated by the fact that they will be anionic and at typical environmental pHs and usually be in a dissolved state as well. So that makes the whole, is it volatile? How does it interact in the air? A fairly complicated question involving aerosols, solids, and the vapor phase. So that's a little bit about volatility. I'm going to spend a little bit of time measuring PFAS because we're talking about measurement of PFAS because, first thing before you regulate, you measure. We've been measuring PFAS in the environment, whether it's the air, water, soil, tissue, name it, for, I would say, close to 30 years now, longer if you think about specific carbon, fluorine, or haloacetic acids. But the concept of PFAS as a measurement is let's say, about 30 years old. And most of our PFAS measurements use a technique called liquid chromatography, mass spectrometry, tandem mass spectrometry. This is very specific, sensitive, accurate measurement for specific non and semi-volatile PFAS. So these are the anionic PFAS like PFOA, PFAS, all those other acids that are of major regulatory concern, especially in the non-air phases. And this is what LC-MS-MS measures. Typically, LC-MS methods can measure up to around 70 or 80 PFAS, depending on the availability of standards, etc. Standard methods, EPA method, we'll talk about that a little bit, will measure up to 40 different PFAS by LC-MS. Advantages is highly sensitive, highly specific. Disadvantage, of course, is you're only measuring what you're looking for. So when you looked at this, list of 7,000, 8,000, whatever number of PFAS, that 40 or 60 PFAS you're measuring is a very small subset of that. So there's different types of techniques to expand that universe. But before I go there, for air, the counterpart, which is GC-MS-MS or GC-MS, using gas chromatography instead of liquid chromatography, is what is typically used for volatile PFAS. So the neutral PFAS or shorter chain PFAS that are typically more amenable to gas chromatography. So for every LC-MS-MS method, There are new GCMS methods and MSMS methods being developed for that different list of volatile PFAS that we'll be talking about in a little bit. But those are target methods. What happens when you need to look beyond those targets? There's a number of different techniques available. We won't spend too much time on those because it's just like we'll be here for days. But the total oxidizable precursor assay, for example, is used pretty commonly in non-air samples because it oxidizes unknown PFAS that are what are called precursors that can transform into carboxylic acids or sulfonic acids over time into carboxylic acids that can be easily measured. So it's kind of an oxidative technique to convert a lot of unknowns into knowns that you can measure and gives you a lower bound of some unknown PFAS. Technique fairly commonly used in the environmental community. Going the completely opposite route and looking at total or organic fluorine, here you're no longer concerned about what type of PFAS it is. The question is there fluorine present in the sample? How much of that fluorine is organic? So there's a number of different organic estimation techniques. And again, not going to spend too much time on those. We'll touch upon some intersection where some of these techniques may be used for air analysis or industrial hygiene as well. The advantage here is that they are quick measures of totals, gives you a total, and the total is always going to be much higher than your target. The disadvantage, of course, is you don't know what you're looking for. In many cases, you don't even know if that total is the relatively harmless inorganic fluorine, your fluoride, your sodium fluoride, whatever it might be, or the organic fluorine that you would consider PFAS. And then another whole and new emerging technique that we won't even talk about is a high resolution mass spectrometry for non-target analysis, where you're using mass spectrometry to look at thousands of different peaks and identifying PFAS, unknown PFAS, and characterizing them. Again, an emerging field at this point in time, mostly in the research and forensics community at the moment, not really much used commercially. The thing about PFAS methods, and this is always a good touch point to confirm that most people are saying, well, measure PFAS. It's not as simple because, as I said, the structures and properties vary so much that what's going to happen eventually once all these methods are developed is that you're going to get this broad swathe of different methods, just like we have for semi-volatiles, volatiles with the TO series, go from TO1 to however many TO methods there are. So that's what's going to happen for PFAS. There's going to be a few methods for semi-volatiles. It's going to be a few methods for volatile PFAS as well. So that's just the little caveat before I begin. One method will not touch, will not even begin to measure all the PFAS that are present. So from current air methods, the first question is, how do you sample? And there's a few different methods for sampling, depending on how volatile the PFAS is. And most of these are going to be familiar for you. PFAS have been sampled using semi-canisters, TD tubes. Passive samplers have been used for PFAS as well. The semi-canister methods are used for very short chain PFAS, like C1, C2, TD tubes for slightly longer chains up to C8 or so. Passives can pick up both volatile and semi-volatile PFAS. Then once you start going off to the right here, you're really focusing on non-volatile or semi-volatile PFAS. So the one fourth from the right here, the X80 puff filters, used typically for either kind of high volume air sampling in ambient environments or using smaller volumes, smaller tubes in for occupational exposure, using an OVS type sampler or similar sampler. But again, these are used for semi-volatile PFAS, using a mixture of different chemistries to capture that PFAS, and then you extract those PFAS off those X80 or puff, and then run them through whatever analysis you're trying to run them through. And then to the right here is what's called a OTM45, which I'll talk about in a little bit. It's a method for semi-volatile PFAS in industrial stacks. So, it's a stack emissions method, similar to a dioxin stack emission method. So depending on the volatility, depending on the type of application, you have many different types of capture techniques. So that's the first challenge here is, do these techniques capture PFAS? And for all of those, you are essentially looking at validation on specific target and analytes to confirm that these sampling techniques are appropriate for PFAS, and also don't introduce background because PFAS, Teflon, a lot of these substances are everywhere, and so background is always going to be a concern as well. So before we really start talking air methods, this is the current status of EPA methods at the moment for most things other than air. There's one air method at the bottom. Because the focus mostly has been on drinking water and waste and fish tissue as well. That's where most of the EPA attention has been so far. There's two drinking water methods, 537.1 and 533. Don't have too much time to go into the nuances and differences. They have different target lists, slightly different methods, slightly different approaches, and they're not always compatible. However, they're both EPA methods and both available for use. 1633 is the most comprehensive EPA method available. It runs 40 targets, and it's going to be used for non-potable water, solids, tissues, and waste once promulgated. It's still in draft. There's a couple of other approaches as well. 8327 is a screening method for PFAS in water written by the EPA. Uses a very simplified technique to get quicker answers, but not as definitive or not as sensitive as your reference methods. 1621 is an organic fluorine method for measurement of PFAS in water. Again, it's in draft, going through promulgation or going through validation at the moment. OTM45 at this point in time is the only published air method for PFAS. As I mentioned briefly before, it measures about 49 different PFAS in air stack emissions, so coming out of a factory stack, coming out of an incinerator stack, that kind of thing. And it uses LCMS, so it is designed specifically for those semi-volatile PFAS that are also the targets in all of these water and solids method, not necessarily for volatile PFAS. That may be more of a concern on the industrial hygiene or inhalation front. EPA 1633 is probably the most comprehensive method at this point in time. So it's a pretty, I'm going to use it as an example of a typical PFAS method. It was developed and validated by one of our labs here, right where I sit in British Columbia, Canada, for the EPA. So it's going through validation at the moment. But that is a typical example of what a 40 target LCMS method looks like, and it's going to be used for all non-potable water, wastewater, surface water, groundwaters, soils, tissues, pretty much you name it, everything non-air and non-drinking water is going to be used using 1633. So the EPA has done a lot of work on getting non-air methods going, but air has not been left behind. It's just a few, I would say, at least 4 or 5 years behind. And again, EPA is fairly active on this front, developing methods, and the ASTM is as well. These methods are fairly complementary. They use similar techniques, and they often talk to each other as well. So ASTM methods will inform what's in an EPA method, for example. So I'm mostly focusing on EPA methods here. There's going to be a method for source air, but using GCMS methods that are going to be more for the, I made a typo here, but it's more for volatile PFAS for emissions like OTM45, which is for semi-volatile and non-volatile PFAS. But again, don't know when that's going to come out. There's going to be a TO15-like method for PFAS, very short chain volatile PFAS using summa canisters, using GCMS. And there's some talk about using non-target approaches as well to get a full picture of all the uncharacterized PFAS. Again, don't know when that's coming out. Some of these have names of EPA numbers attached to them. One of them is OTM49, the other one is 50. Never remember which one is which. There's a couple of other approaches as well. There's going to be a kind of a real-time measurement by mass spectrometry that can be in the fields that I believe it's called CIMS. Again, coming soon is what the EPA says about it, so stay tuned. A lot of this is under active development in the EPA at the moment, but usually information is slow to come out till we have some, till the method's actually published. There's going to be methods on semi-volatiles and ambient air as well, based on the high volume sampling type method that I showed you previously, X80 puff, that kind of thing. And especially for ambient and occupational exposure, there are two methods coming out using either summa canisters or sorbent traps. But again, all of this is to be decided. So we're still waiting on details on what the EPA is putting in these methods. And there's a link here. Once you get the presentation out, you will see these methods, at least for the statuses. The EPA is working on, and I won't spend too much time on these slides. They are generally, just to want to mention that the PFAS is probably the single biggest focus of EPA regulatory, just eyesight at the moment. So there's action on every front, whether it's drinking waters by the MCL, discharges in wastewater and in leachates and industrial dischargers as well. Air and radiation is a little further behind. The framework is still being built, but there's a little bit of focus there too. OSHA has not really taken action. I did a brief search, and PFAS still stands for fall arrest system. So again, still not much action going on in OSHA. NIOSH has been working quite a bit, especially on the research side. They have a PFAS page. There's a good introduction to occupational and health risks of PFAS, especially on the focusing on occupational exposure. So I would definitely urge you to check out the website, but NIOSH is more on the research side, OSHA is more on the regulatory side. So we'll see how that all works out in the next few years once the air and industrial hygiene parts of the regulations start really going forward. Right now, still kind of in flux. Don't want to spend too much time on this. Just want to leave you these as references. Major focus on setting maximum contaminant levels for a specific PFAS in drinking water. 6 PFAS at the moment, and you can see that these levels are very low. They're going to be set, especially at around 4 nanograms per liter is the proposal. Very low. This is typically background, or a little higher than background. So again, it remains to be seen how all of this plays out once all of these comments have been received and processed by the EPA. Not gonna skip over that in the interest of time. The NPDES, or National Pollution Discharge Elimination System, regulates PFAS at the source. So publicly owned treatment works, wastewater treatment plants, industrial dischargers. So this quarterly monitoring being set up for PFAS in that area as well. Again, PFAS have not been officially designated as hazardous, so all of this is going to become mandatory as soon as some of these specific PFAS become designated as hazardous. A little bit on the air and industrial end of things. There's a few states, and this is all summarized both in the ITRC and this excellent review paper by Paris Devil. I'll touch upon that in a second. That are starting to regulate exposure indoors and in occupational settings. Most of these are based on inhalation, and most of these, especially from Minnesota and Michigan, the ones that have regulation have backed into inhalation RFCs using extrapolation from an oral RFD. And this kind of points to the paucity of research on, especially the lack of research on regulatory, that informs regulation on inhalation and dust exposure. So while a few of these states have some of these numbers in place, most of them have come primarily from the water end. And Texas, I believe, has some of the lowest numbers and some of the longest lists here as well. But again, this is a constantly evolving field. So if you ask me next week, something has changed. And typically the ITRC is a good source for that, though they're still working on their occupational areas here. Do you want to talk a little bit about exposure? And for the next, little bit of this presentation, I'm going to start with residential air exposure because that's where there's been a lot of measurements starting, I would say, even 15 years back. This is data from Winkens et al. And you will see in a lot of these slides that are coming up, I will present data from volatile PFAS. So what you'll see on the left here, fluorotelmer alcohols, fluorotelmer acrylates, ethanols. So these are all PFAS that are neutral, not typically uncharged species, and therefore they're volatile or at most, mildly semi-volatile at room temperatures. So you'll see this pattern as I go through some of this exposure data, that a lot of these PFAS, the volatile PFAS that you measure, are going to be orders of magnitude higher than some of these semi and non-volatile PFAS. But you will also see that these semi and non-volatile PFAS, your PFOA, your PFAS, these are the focus of most of the research on toxicology, most of the research on most of the regulatory action, especially in the non-air areas. So this, in some ways, excuse me, is one of the first disconnects when you start looking at exposure versus toxicity, because a lot of times what you're measuring is not typically what you're doing the tox studies on. There is another wrinkle here, of course, is that a lot of these PFAS that you measure in the non-volatile, in the volatile regime, so your fluorotelmer alcohols, your acrylates, your ethanols, they will transform into non-volatile acids, either biotically or abiotically over time, sometimes in vivo as well, so in the human body. So the exposure becomes even more complicated because you're measuring all of these volatile PFAS. They're also transforming into the more toxic or the ones where you have more toxicity data over time. But this is a good example. So this, in indoor children's bedrooms, for example, you're seeing these fluorotelmer alcohols that are present ubiquitously in packaging, in waterproofing treatments, in a lot of other, in household PFAS uses are typically found at high concentrations, so in high nanograms per meter cubed to mid nanograms per meter cubed, whereas your non-volatile PFAS are going to be in the low to mid picograms per meter cubed in the air. Measurable, but fairly low. So we'll come back to see this again and again. When measuring grass phase, volatile PFAS are always more predominant, but a lot of the data you will see is on the non-volatile PFAS. Carpets at daycares is another good example. In this case, they were measuring dust, and dust represents particulate exposure. So the semi and non-volatile PFAS here was also predominant. So you're looking at total carboxylates, total sulfonates, total fluorotelmer alcohols. Again, fluorotelmer alcohols range from the very short chain 4,2, which is very volatile, to 10,2, 16,2, which are fairly non-volatile. Think about it's like an alkane chain. The longer the chain, the less volatile it gets. So again, measuring these carpets and dust, PFAS are used routinely in waterproofing and Scotch guards, stain guards, whatever you call them, depending on branding. So a lot of this, especially for children, pets, this represents a significant PFAS exposure, and there's been quite a bit of work done on PFAS exposure from dust and particulate exposure, especially in the household realm. But again, 1 to 100 or 1 to 1,000 nanograms, depending on where you're looking at, whether it's a specific PFAS or the total PFAS. And again, another point to note before I move on is that almost all of this is target PFAS, meaning you're looking at specific lists ranging from 10 to 40 or 50 PFAS. And in many cases, this target PFAS is a small fraction of what you typically measure, because a lot of these PFAS are unknown, uncharacterized. So again, something to keep in mind. So that was about household exposure. It is ubiquitous, typically characterized by fluorotelmer alcohols, mostly coming from waterproofing treatments and carpets and houses and food packaging. When it comes to worker exposure, the obviously, because PFAS is used quite significantly and ubiquitously in industrial setting, the exposure pathways and the types of PFAS you get exposed to are quite a bit more varied. Before I really get going, a little bit on the ACGIH TLV. So the ACGIH has set up TLVs for PFAS. Of course, these are guidance values not enforceable by regulation for 3 specific PFAS. And a lot of these come from the earlier days of especially fluoropolymer manufacture. So Teflon, just polytetrafluoroethylene, when heated or or agitated violently and also heated, can release fairly toxic gas called PFIB. And this is the source of, if you've seen, on YouTube, birds dying in houses because of overheated Teflon pan. That comes from PFIB. So there's a ceiling on that published by the ACGIH. Perfluorobutyletylene, again, is a solvent used in polymer manufacturing and food contact packaging. There's a TLV on that as well. PFOA listed as ammonium perfluorooctanoate, it's a salt of the anion, has a TLV listed in the ACGIH as well. So to my knowledge, this is the only TLVs listed. If anyone has any more, please list them in the chat. We're glad to learn more about this as well. Again, emerging field as air regulation gets, as air research gets more rounded out and as more regulation comes on board, we expect some of these TLVs, some of these guidelines, some of these regulations to get tighter and get more specific on the type and number of PFAS that are being regulated. Occupational research, and when I started doing lit review for this, I was thankful for these two review papers that came out pretty much within 6 months of each other in the last year or so. First by Paris de Villa et al. And second by Christensen and Calkins, both focusing on reviewing and collating a number of different articles and studies that have been done on occupational exposure over the last decade or 2 decades. Most of these studies focus on fluorochemical workers, especially in the early times when fluoropolymer manufacture and exposure was a major issue. Firefighters, of course, because of exposure to AFFF or aqueous film forming foam containing PFAS. Ski wax technicians, because they're constantly exposed to high levels of PFAS in the ski waxing process, because the waxes have high levels of PFAS in them. A lot of this work has happened indirectly using serum monitoring, so measuring PFAS directly in people's blood, workers' blood. This presents an aggregate overall kind of almost a lifetime exposure. So sometimes it's hard to understand what you're specifically being exposed to based on your serum numbers, because a lot of these, it's the same PFAS you're measuring coming from multiple sources. Many of these studies, luckily, have started to focus on monitoring of workplace air. But again, there are some nuances on how it's measured. Is it measured in the room? Is it measured in the breathing zone? Because that makes a big difference, big impact on how much a worker is being exposed to with the PFAS. And again, the major issues always come down to which PFAS are we measuring? Are these semi-volatile and non-volatile PFAS, which are of high toxicology and regulatory implications, but are going to be found at low levels, or the volatile PFAS that are going to be found at high levels, but are not as commonly measured? And then again, these are specific populations. What other populations are more vulnerable? We're not quite sure. So a lot of unknowns, a lot of uncertainty in much of this data. But there's some interesting things that we've learned from a couple of these studies. And this is a great chart from Christensen et al. Again, listing the type of worker, and these are different studies over time, and the concentration in serum. So these are measurements in serum. So you can see, especially these are listed, from the bottom up time-wise, and you can see that the levels measured in serum are, especially for these particular target PFAS, have generally decreased over time, only because these really big numbers to your right here, and log scale, remember, so these are really high numbers, are early on. In fluoropolymer manufacturers, chemical production plants, where exposures have been very high. And so the phase out of some of these more toxic PFAS like PFOA, you expect these levels to go down over time. But you can see a couple of these high levels here. Ski wax technicians seem to be the highest here, where some of these are still ongoing exposures, and so those you would want to be concerned about. But overall, the general trend is that for PFOA and PFAS especially, these longer chain PFAS, the trends have decreased over time because these chemicals have been subject to a phase out. They're of course being replaced by shorter chain PFAS, other PFAS. So again, lots of unknowns here on what we're measuring, and what we're measuring drives some of these numbers. Looking at dust and air, especially, and these charts are from Paris de Villa et al. Again, the same trend you see is that ski wax technicians have the highest PFOA exposure. But again, as these ski waxes transition, hopefully, to a shorter chain PFAS or non-PFAS, you're hoping to see less and less exposure over time. But there are some other areas as well, textile manufacturer, where you might exceed an RFC or a reference dose, reference concentration. So lots and lots of information. But overall, in many cases, especially for some of these PFOA, for example, you're starting to see some of these are hopefully reducing over time. But again, the question always is, are these the appropriate PFAS to monitor? So I'm going to come back to that again and again. When you look at fluorotalmer alcohols and air concentrations, dust and air concentrations, so remember that the fluorotalmer alcohols are the more volatile PFAS, so you're expecting to see these at much higher concentrations, and that is true. The ECHA, the European Union, has reference concentrations for 6,2 fluorotalmer alcohol, which is usually the single highest FTOH, has multiple uses, multiple also kind of multiple places where it's an impurity or an addition. So you expect to see this at fairly high levels in indoor air, and sometimes it does as well because it does partition. But again, not that many studies, especially when you compare it to a serum. So this is an area where I think in the next 5 years or so, once better methods are coming on board from the industrial hygiene community, from the EPA, we're going to start seeing a lot more data coming through on these volatile PFAS that, I remember if I told you, will transform into semi-volatile, non-volatile organic acids over time, which are the focus of regulatory attention. So these are, you have to look at these individually as PFAS as well, but also as precursors to more toxic PFAS. But again, the message that I'm going to leave you with, and I think this is my last slide, is that the volatile PFAS universe is still fairly poorly mapped, especially compared to the semi-volatile areas in drinking water, soil, and fish. And this is where I think we in the industrial hygiene community have a big role to play in, especially in getting these methods on board, starting to measure these PFAS, looking at what other setting PFAS are used, where you suspect PFAS use, and starting to measure there, especially worker exposure, especially inhalable worker exposure, where it's a fairly relevant measurement, and then understanding and then filling these gaps as these EPA and other reference methods come on board. Wasn't my last slide. So wastewater and landfills are a fairly significant source of PFAS as well, especially in the air, the aeration and the aeration part of the wastewater treatment plant. Wastewater treatment plants are passive receivers of PFAS. They take in PFAS from multiple sources, and we're not going to really touch upon this here, but they also convert some of these volatile PFAS into non-volatile carboxylic and sulfonic acids through the aerobic transformation process. So again, you will see that these target PFAS, especially fluorotalmer alcohols, and some of these, especially the fluorotalmer alcohols, are orders of magnitude higher in these wastewater treatment plants and landfills compared to these non-volatile and semi-volatile PFAS that we're measuring more typically in the water and solid phase. Same story that you measure in other environments as well. So just, yeah, this is a fairly important point, especially in the aeration chambers, especially depending on the type of PFAS used. PFAS aerosol exposure can be a fairly significant source, and we need much more measurement here, especially more relevant measurement and more recent measurement. So that is, it's going to conclude with that, this conclusion slide. I touched briefly upon regulation. PFAS is being regulated on multiple fronts. If you ask me next week, something new is going to come out. So this information is ever evolving. We are a few years behind, especially on the industrial hygiene and air measurement side of things, but hopefully catching up. Different PFAS to measure in air. So something that we really need to pay attention to when we're designing studies, we're looking at methods, is that we have to look at volatile PFAS because they're going to be at fairly high concentration. And as I mentioned, methods are still in development, but especially for the air, but other matrices are becoming standardized with the drinking water and non-potable water. So the EPA is working really hard, and other agencies as well, to get these methods going. So with that, I'll leave you with this page here. the presentation is going to be shared, so please click on this link. This is our landing page for all the PFAS analysis that we do over at SGS. So, and you can always find me on LinkedIn and share contact information here as well. So with that, I look forward to questions.
Thank you, Bharat. It looks like we have about 15 minutes or so for questions. There's quite a few already, so please know that if we don't get to your question, we'll be sure to share it with Bharat and Galson to follow up with you later. Our first question is from Matt. He actually has two questions. He asks, why can't drinking water samples be analyzed under EPA 1633?
So that is not a technical issue. The method was actually validated in every type of water. So you can run a drinking water method by 1633 and get a perfectly reasonable result. The reason for that is that the EPA sets up its drinking water regulations differently from its Clean Water Act regulations. So drinking water is mandated by the Safe Drinking Water Act. Different agency or different part of the agency, they have their own methods for drinking water. The Clean Water Act regulates all other water and sometimes and some parts of the solid waste stream as well. And the Office of Water runs that. And the Office of Water is who's responsible for all the non-potable water methods. So you see this quite frequently in the EPA regulatory landscape, is that even though technically these methods are identical and can be used for measuring drinking water as well, just because of the regulatory setup, they unfortunately have to be run using two different methods. Hope that answers that question.
All right, thank you, Bharat. Another question about methods. Will EPA 533 and 537.1 be improved to include more PFAS?
I believe the EPA is working on improvements for those methods. They are, I think, looking at adding more PFAS. Has not come out of the detailed scope yet. So once we see the detailed scope of improvements, I think we can all, we'll just have more light on that. But I know they're working on improvements to the method in general.
Okay, thank you. Mitch was asking if you had anything more to say about thermal decomposition byproducts such as hydrogen fluoride and PFIB.
Yeah, I mean, that's just that is such a hot topic of research again, because PFAS are very hard to destroy. So incineration, pyrolysis, other thermal methods have been the first targets. But the concern, of course, is are you completely mineralizing the PFAS? So are you producing HF and carbon dioxide or other other non-PFAS entities, or are you producing these and some shorter chain PFAS like carbon tetrafluoride, other really ultra short neutral PFAS. There's been some research from the EPA indicating that incineration is not always complete, even when run at 1,000 degrees. But there's also been some research from other people saying that no, it's complete. That is why there's a big focus on these methods for ultra short volatile. So the Summa canister methods for CF4, C2F, C2F6 and more. So that's again why that's such a big topic, because we're not sure at the moment. And again, there's been a lot of research studies on this, but there are gaps because you don't know the capture efficiency, you don't know if you're measuring the right targets. And that's why the EPA is also working on these non-target methods to capture all fluorine-containing entities, not just targets. So if you ask me next year, hopefully there was going to be more light on that.
Okay, thank you. Amber asks, you spoke about state regulations. Do you have anything to say about international regulations?
Yeah, I mean, again, really hot topic depending on the jurisdiction. The European Union is probably the furthest ahead on PFAS, starting with their definition. But there's a lot of debate. The EU recently, and states in the EU, different member states have different regulations on PFAS in drinking water and other sources, different lists, different numbers. A lot of the focus in the EPA has been on in Europe has been on source regulation and source control. So there was a proposal by the ECHA to, for example, to eventually phase out all non-essential use of PFAS. That came out, I think, late last year, earlier this year. They have since walked back from that due to significant pushback, but a lot of international regulation has focused a bit more on source control rather than end regulation, which is typically how North America works, is more on the end regulation end of things, but a little bit on source control as well. So that answers your question. It is evolving internationally just as it is domestically.
Okay, thank you. Lindsay asks, do we have commercial options for measuring 6,2 FTOH in water?
Yes, we do. There's a number of labs that measure 6,2 FTOHs in water. SGS is one of them. There's a few other commercial labs that do as well. So, but if you want to hear more about it, just reach out to me and be glad to tell you more about how we measure FTOHs. But there's definitely options available.
Okay, and Maureen asks, are there methods currently available or under research for PFAS mitigation?
Sorry, is it litigation or mitigation?
The mitigation.
Oh, yes, absolutely. So it's a very good question. Most of these methods that the EPA has put out the focus has been on environmental matrices, so measuring in soil, water, air, you name it. When you start looking at remediation methods or mitigation methods, some of these matrices are different. So, for example, for drinking water, you use granular activated carbon or ion exchange to capture the PFAS, entrain it, and then you destroy it some way. First off, you have to measure the PFAS left over in that ion exchange resin. Typical methods don't always work well. So we in the lab community, SGS in particular, are currently working on with different collaborators, and this is an area of research focus at the moment, is to tailor some of these established methods for samples coming out of remediation. And we're working on a couple of different federally funded projects at the moment, but nothing standards coming out yet. On the air front, similar. I alluded to this briefly, right? If you're looking at incineration or pyrolysis as a mitigation method, you need to confirm all that PFAS is mineralized. Nothing really standard available at the moment, but the EPA is working on that.
Okay. Matt asks, do you have any insight on PFAS exposure to workers around landfills?
No, it's a great question. Landfills, and we've done a lot of work in landfills recently, mostly focusing on measuring the PFAS in the landfill waste itself. Extremely high because of carpets, food packaging going in, and landfill leachate as well. Fairly high because, as you know, PFAS never get destroyed. They're transforming in the leachates into carboxylic acids and sulfonic acids over time. I need to go back to our literature, but I don't know if there's been direct exposure estimates for workers actively working in the landfill sites. I will bet you that if you measure it, you will definitely measure the usual suspect, the fluoroalkyl alcohols, some of the carboxylic and sulfonic acids as well. Anything that's used in food packaging, anything that's used in carpets is going to end up in a landfill eventually. And so all that PFAS is a source of exposure. And there's been some older studies that I did mention that on one of the earlier slides, but that's older work, and a lot of that needs to be replicated.
Okay, thank you. A couple of people are wondering why tea farmers were investigated for serum levels of PFAS.
I don't know in that particular study because I haven't seen it, but PFAS are used in many especially in agriculture, as what the EPA or manufacturers call inert additives to PFAS. So a pesticide or fertilizer may contain a PFAS added that is not listed on the label, not listed in the ingredient, not part of the toxicity profile because they've been considered inert. So they're not the active ingredient when you think about a pesticide. But that is my guess as to why that may have been studied. But I don't know. I'm not 100% sure as to why that might be in the case. But there's a lot of attention now on which pesticides formulations may contain PFAS, which fertilizer formulations may contain PFAS. A hot topic of emerging science at the moment.
Okay, thanks, Bharat. Another question here, Ivan asks, if the science of volatile or neutral PFAS is already known, is there a need for more data?
Oh, great question, Ivan, and hello. I think the science is known. The data gaps are still present because while we know I think we have a good handle on where PFAS is present, or a relatively good handle. So what kind of products may contain PFAS, what kind of manufacturing techniques, or what kind of manufacturing industries, what kind of uses are more of a concern. What is missing is that actual exposure data. Is like we have drinking water measurements for PFAS in pretty much every community in the United States at the moment. That is the level of PFAS. That is the level of PFAS comprehensiveness that's present in drinking water. I bet you nothing similar to what's on the occupational health exposure. And these are direct exposures. Remember, these are direct exposures at levels that are orders of magnitude higher than what you'd be present in drinking water. So for me, the case is clear. Occupational PFAS exposure is really important, and the only way you get more information is by measuring it more in more places, in more use cases.
Okay, thank you. Another question, someone asks, are there sampling and methods for ACGIH TLVs such as PFIB?
Good question. Not to my knowledge. There might be at certain higher levels. There's definitely research and reference type or non-reference methods available. To my knowledge, there are no standard methods. PFOA is the only one for which there is an air method, but that's OTM 45, which is semi-volatile and stack. So that's again the big gap is that there are these to set exposure limits, to set TLVs, we need standard measurements and standard methods, and that's where hopefully in the next year or two, we're going to see a lot of progress from the EPA and other regulatory agencies.
Okay, Bharat, and I think we're close to the top of the hour, so we'll do one more question. A couple of people are interested in your understanding of dermal absorption health effects from constant contact with consumer products like rain jackets.
I think it's a great topic of further study. There's been a few review papers. There's been quite a few research articles on the percentage, and the Sunderland et al. Did try and summarize some of that. One of the review papers I showed in my earlier presentation, and that's probably a starting point to look at the studies that consider dermal exposure. It appears the EPA and other agencies are not considering it a major route based on some of these studies. But again, it would be interesting to see how all this data is and how it's evolved over time, and what the current state of science is. A lot of these DWR use of water repellents, they are typically fluoropolymers with low bioavailability. So that may have been a reason why some of these DWRs are not a big source of exposure. However, again, it really depends on details and what the PFAS uses. So probably, again, I will leave with more studies needed.
Okay, unfortunately, that's all the time we have for today. If we did not get to your question, I'm sorry about that. We'll be sharing all the questions from today's event with Bharat and with SGS Golfin. My thanks to Bharat Chandramouli for his presentation and for answering all these questions, to SGS Carlson for sponsoring today's webinar, and to all of our participants. Please join us next week for a Synergis product demo on October 17th. Details are available at aiha.webvent.tv, and have a great rest of your day.
And thanks everyone for the engaging questions. We'll get back to you on the rest of the questions soon as well. Thank you.
This concludes today's webinar. Thank you all for attending. The recording will be available at aiha.webvent.tv. We will send all registrants an email tomorrow with that link. And please visit our event calendar to sign up for a future webcast.